Hey guys, it's Dr. Brown with Kubo Math coming to you from Tarlac City, Philippines, and tonight it's Calculus 1 second derivative test. For those of you who haven't seen the video first derivative test, or you're just not familiar with first derivative test in calculus, you may want to close down here and go to that video, look at it, and then come back. So otherwise, let's get after it. Okay, to the right-hand side, you know me, I'm a rules guy. There's three things that you get, or at least I can get, from a second derivative test. Two of them I like really well. One of them, okay, we'll talk about it, but I don't use it for that, but that's okay. All right, one is the inflection point. Let's say I have a function that's running along like this. And let's say that's a cost function. And let's say leadership says, well, we want our profitability to be somewhere around that much. And if our cost gets above that, that's a bad thing. They're going to chop off your head. Okay, hopefully they don't do that. But as leaders or executives in a company or line workers, it doesn't matter. Our job is to deliver for the deliverables of the organization, keep them, help minimize their risk of things going bad, and that ensures that we can maintain employment. Okay? So inflection point would be this point in this function where I go from, you see it's somewhat concave upward, or downward, sorry. So it's concave downward, and somewhere along in here it makes a change and starts going upward. So here we are going up at this point. Well, that particular point would be of great concern. Where did my expenses that I thought I had in control make a change and start going crazy? It may be you want to look at what was happening at the business during this time, productivity, scrap, market fluctuations, COVID-19, or whatever it happens to be. What happened with driving this up, and knowing when it made that turn allows you, if you know that inflection point, to be able to analyze it. Now that happens when f double prime of x equals 0. So if you have a function, which we have one here, and we'll take the second derivative of that in a moment, but if you take that second derivative, set it equal to 0, you get a value of x that allow, or multiple values that allow that to be 0. Now it could be undefined at that point also, so keep that in mind. But if we know that point, that's the inflection, then we can look to the left or right of that to see if it's concave up or down. F double prime of x, if it's greater than 0, it's concave upward. So I would know in this case f double prime of x is greater than 0. It's positive. In this case, f double prime of x is less than 0. Now, the value of x that I'm comparing it to would be the value that set it equal to 0. So I'm looking just to the left and right of that, and I should see it change signs. In this case, it's going to be less than, the sign of f double prime would be negative here, be positive here. Okay? Very similar to the first derivative test where we set it equal to 0, found a critical value that solved it, and then we could look just to the left and right of each of those critical values to see if the function was increasing or decreasing on each side of that critical value of c. Okay, if that's the case, I had a relative maximum when x equals c. Okay, if I had the opposite of that, now I had a decreasing function. So I'm negative here, positive here. So it's just, you're looking at, since it's the first derivative, it's the slope. So if I had this situation, I had a relative minimum at x equals c at this point. So relative maximum, relative minimum. You can do the same thing with the second derivative test by looking at f double prime of c. So you have to solve for c in the first derivative, set that into the second derivative test. Now this is why I don't use it, okay? But I'll share it with you. If f double prime of c is greater than 0, it's a relative minimum. If f double prime of c is less than 0, it's a relative maximum. If f double prime of c equals 0, the test has failed and you need to revert back to the first derivative test. Okay? However, for me personally, I like to look at the concavity and the inflection point. That has great meaning. Now, while I'm there, obviously sometimes, yes, I'm going to go ahead and may work this test. But the problem we have tonight, you may see, oh, there's a challenge in that. Okay, so enough of this. Let's get busy on the problem here. I may be out of the screen just for a little while. All right, f of x, that may increase the value of the, of the video. Oh, by the way, I have a little saying at the bottom that I always mention at the end of the videos. Why am I doing these videos? I have spinal stenosis and can't work anymore. I'm 64. I've been off work for 4 years. And you know, I have a PhD in reliability engineering, and I just feel I want to share something with you. I grew up on a farm, a hog farmer, diesel mechanic for many years. Went to school late in life and just went from, you know, humble beginnings to ultimately being a chief technical officer and senior vice president for various companies. So again, I want to share these things with you so that together we can build a better tomorrow, and do that by learning math. Do that through math. Math changed my life. I want to help it change yours. Okay, so I'm going to stretch out here. Let's take the first derivative. Yes, I'm off the screen, I know. Okay, f prime of x equals, bring the 4 down, x to the 4 minus 1, be 4x cubed, minus, bring the 3 down times 4, that's 12x squared. Okay, now let's take the second derivative. Take the derivative of the first derivative, that's the second derivative. So 3 times 4 is 12x squared, minus 2 times 12 is 24x to the 2 minus 1 is 24x. Now it said if we wanted to look at the inflection points, we needed to set the f double prime, set that equals 0, and find values of x that solve for that. So in this, we're setting that equal to 0. So hey, when in doubt, do what? Factor. All right, I can get a 12x out of this. So let me pull the 12x out, and that equals x minus 2. Is that right? Let's use the distributive property. 12x times x gives me 12x squared. 12x times a negative 2 gives me negative 24x. All right, so what does this mean? If I set that equal to 0, well, x could equal 0, or x could equal 2. Okay, let me put that up here. Well, I'll leave it. No, I need to get it out of the way. Let me get it over here. X equals 0, x equals 2. Can you still see that? Yeah, okay. Okay, you may be thinking, big wooey, what does that mean? Okay, look at our rules. Now, if we wanted to know if the function's concave down, concave up, we can do that by taking these values, x equals 0, x equals 2, looking just to each side of those and see if f double prime is greater than 0, then it's concave up. So we'd have f double prime greater than 0. F double prime of x is greater than 0, and that's about as sloppy as you can get. F double prime of x greater than 0, or concave up. F double prime of x less than 0, or concave down. Okay. Now then, our interval, it's very similar to what we did with the f prime of x. Let's look at an interval. X has to be greater than minus infinity, but less than 0. That was my first value that set this equal to 0. Okay, x could be greater than 0, but less than 2. X could be greater than 2, but less than positive infinity. All right. Now, what's our test value going to be? X equals something that we're going to plug in this equation and see whether it's positive or negative. Okay, so if it's less than 0, let's just say -1. Okay, in this case, it's greater than 0, but less than 2. We'll just say it is equal to 1. Okay, and this one's greater than 2. So let's just keep it simple. We'll just say that's equal to 3. All right. Now then, f double prime of x. So let's take the -1 and put it in here. And we're just looking for the sign. We're not really concerned about the actual number. So -1 times 12 gives me a negative. -1 minus 2, well, negative minus a positive plus a negative, it gives me a bigger negative. So negative times negative is a positive. Okay. All right. Now then, let's take the 1 and put it in there. So I have 12 times a positive 1, which gives me a positive. 1 minus 2 is still a negative. Okay, and positive times negative gives me a negative. Okay. And this one, x equals 3. So I've got a 12 times 3, that's positive. 3 minus 2 is 1, that's positive. Positive times positive gives me a positive. Okay, now then, in this case, f double prime of x is positive, so it's telling me that this thing is concave upward. So it's concave upward. This one is negative, so it's telling me it's concave downward. And this one is upward, so it's telling me that, or positive is telling me it's concave up. Now you can see here where x equals 0, I go from one level of concavity to another, and then after I get on the other side of where x equals 2, it goes the other way. Okay? So it's telling me that this thing, the x equals 0 is an inflection point, and x equals 2 is an inflection point because the concavity changed. Now, to do the relative minimum or maximum, I need to go back to this f prime and solve it to find c. So let's set this guy equal to 0. We pull him up here. 4x cubed minus 12x squared. And let's set that equal to 0. Well, I can, when in doubt, factor. Okay, 4x squared I can pull out. So that's x minus 3. 4x squared times x gives me 4x cubed. 4x squared times -3 gives me -12x squared. Okay, so x equals 0, x equals 3. Hey, all right, so we had some of that already. All right, let's now take and plug in x equals 0 into our equation into f double prime. Now you'll notice if I plug 0 into this, I get 0. And it says f double prime of c, if it equals 0, then the test for a critical or relative minimum or maximum has failed. So that didn't tell me anything when I put in x equals 0. My test failed. Okay. Now we had x equal 3 in there earlier, so we had a positive. It was positive, so it was telling me f double prime of 3 is greater than 0. So when x equals 3, that's a relative, it's greater than 0, that's a relative minimum. Now, you know me, I like to challenge that. Okay, we know inflection points. We're going up, we're going down, we're going back up. The test failed at x equals 0. It said it didn't know if it's a relative minimum, maximum, or what. But it did say I had a relative minimum at x equals 3. All right, so I'm going to erase this. Well, let's see if I have enough cord here. Well, I better erase it. Let me get back over here. I wish I had about a 20-foot cord. All right, I don't guess you have to have a snapshot here, so let me write to the side. We had at x equals 0, test failed. The f double prime of c equals 0. It failed. Okay, at x equal 3, it was saying it's a relative maximum or minimum. Relative minimum. Okay, what else did we know here? Inflection points. Inflection points was at 0 and 2. All right, that's what we've learned so far. All right, I'm going to erase this. And we're going to do the first derivative test, same as we did recently. So now it's f prime of x, the sine. Okay. All right, so now we had x equals 0 and 3. All right, so we've got x has got to be greater than negative infinity, but it needs to be less than 0. So we're just going to say x equals -1. And you may be thinking, oh, we just did that. But we did that in f double prime, not f prime, which is what we're doing now. So now x is going to be greater than 0, but less than 3. X is greater than 3, but less than positive infinity. Okay, so in this case, x is less than 3, greater than 0, could be x equals 1. Well, similar numbers we had before, isn't it? Except in this case, instead of x equals 3, it will say x equals 4. And we're putting this in this one right here. Okay. I get it down a little bit. 4x squared times x minus 3. And we just want to know the sign. That's f prime of x here. All right, x equals -1. -1 squared is a +1, so this is positive. -1 minus 3, it gives me a bigger negative number, so that's negative. Positive times negative is negative. So I know that function is decreasing as I'm getting, when I'm running, it's decreasing, it's running like that. All right, let's look on the other side here. X equals 1. Okay, 1 squared is 1, it's positive, times positive 4 is positive. 1 minus 3 is negative. Positive times negative also is negative. So the function is still decreasing. It didn't change at all right through there. Even though I had a root that made this equal 0, and I haven't graphed the function, but maybe, maybe it looks something like this. I don't know, and this is 0, the point 0. It's not a relative minimum, but there is a derivative there. Okay? That could be the case. All right. Let's let x equal 3. So 3 squared is a positive times 4 is positive. 4 squared is positive times that's positive. 4 minus 3 is 1, that's positive. Positive times positive is positive. So what does that mean? I was decreasing on this side. I'm increasing on that side of 3. Wow, that's a relative minimum at x equal 3, which is exactly what we had when we looked at the second derivative test. For me personally, as I mentioned, I like to use the inflection points and the concavity of the, of course you have to get the concavity to confirm that the inflection point's the right point. I guess one day maybe I'll trust it and not look just to the left and right, but I seem to always do that. But I like to use the first derivative test to do this piece of it, because if I'm looking for a relative minimum or maximum with the second derivative test, there are times when it fails, as we saw here earlier when we looked at it on each side of 0. I mean, we had f double prime of 3, I think it was, or sorry, f double prime of 0 came up to be 0. F double prime, you put 0 in here, yeah, it comes out to 0. So, and since that was one of our roots of f prime of x, the first derivative, then it set the second one equals 0 and the test failed, and I have to go back to the first derivative test anyway. So, okay, that was the second derivative test, looking at inflection points, concavity up or down, and looking at relative minimums or maximums and the associated rules to do each. Hopefully this has been good for you. We'll keep rolling along. Not sure what the next video will be, and it may be just go back and work some problems where we're picking out first and second derivatives. That's probably what I'll do. We need to practice some. So, okay, why are we doing this? Just like it says at the bottom of the video there, together, let's build a better tomorrow, and let's do that through math. So that's all for now, and we'll talk to you next time. Thanks.